Hello, in this second video on section 10.5, we're going to talk a little bit about the theory behind the heat equation and solutions to the heat equation. So what we've done so far in this chapter is we've been able to found formal solutions to the heat equation and problems related to it, to the heat equation, which means that we have expressed what the solutions would look like in the form of series of exponential and trig functions. So let's see, and trig functions. So sometimes you might hear someone say, oh, well, let's prove something formally, which means that you're being very formal about it and going through all the details and being very careful. The use of the word formal is actually a little bit different here. Let's erase this S over here, formal solutions. What formal means here is that we're actually talking about the form or the shape of the solution, but we are leaving out a lot of the details. And so what we haven't done yet, we would still need to prove that those series converge to a function. So they need to converge to something that actually, and then that thing that they converge to actually needs to be a solution, which is a solution. So that's not trivial, and it is out of the scope of the class. That's not what we're going to do in this video. So you might think that we actually have already talked about it. We talked about how Fourier series converge to a function, to the function that they're associated with under certain circumstances. That's a little bit different than what we're talking about here. While we use the Fourier series, we actually found a different series solution to the equation, and we don't know that that converges to anything. And if it does converge, we still sort of need to check that what it converges to makes sense as the solution to the equation. In any case, other textbooks do have proofs of the existence of a solution to the heat equation in the form of the solutions that we found in this class. So in the study of differential equations, like we've talked about before, we're interested, not only is there a solution, but we're interested if that is a unique solution. So assuming there is a solution, is it unique? We have found the form of one particular solution. Like we came up with a formula to say, if this is the problem that you have, then, just compute these coefficients and blah, 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 and then here's the solution. And so that might make it seem like that could be the only solution, but we actually haven't ruled out the possibility that there's some other way to find a solution. So in this video, we're going to show that the heat equation can have at most one unique solution. So first we're going to state another theorem called the maximum principle. Maximum principle for the heat equation. So let's let U be a solution to our heat equation. So let U be a continuously differentiable function, which satisfies the heat equation. So that looks like du dt equals some beta d squared u dx squared. And the boundary conditions, u of 0t equals u of L of t equals 0 for t greater than or equal to 0. And so we note here that we have no external heat, that's an L, heat source. So if we think about the physics of this situation, let's say that the wire starts off where one end is really hot at, part of it is at 100 degrees and then the rest of it is cold. And you would imagine that maybe some of the warm parts would cool down while the cool parts would warm up, and you'd probably end up with like an average temperature across the whole thing. But what's not going to happen is that you're not going to have any part of the wire suddenly shoot up warmer than it has been. So the way that we're going to say that mathematically is that, let's do that in blue, then the maximum value of the whole function, u of xt, attains its maximum value at t equals 0 for some x in 0 to L. And then another way to say that is that the max over all time and all x's of u of x and t is going to happen at some point at some x, but at let's see, u when t equals 0. There we go. So the largest value that u ever takes over all time and all space is going to happen when t equals 0, because you're never going to spike up higher than the highest temperature that you had at the very start. So this still would require a bit of proof beyond just the physical intuition, but we're not going to do that here. We're just going to take that physical intuition and then use this statement to prove our uniqueness. Okay, so now our next theorem is on the uniqueness of solutions. So we say the initial boundary value problem, and we'll write out our heat equation again, du dt equals beta d squared u dt or dx squared between 0 and L and t greater than 0. Our boundary values, and our initial condition. So our statement here is that this problem has at most one continuously differentiable solution. And now we can prove this using the maximum principle that we had before. So the way that you prove a uniqueness statement is usually by assuming that you have more than one solution. So we will assume that u of x and t and v of x and t are continuously differentiable solutions to the problem that we wrote up before. And then we'll let w equal u minus v. So the goal here will be to show that w is in fact 0, that it's 0 for all x and t, and that would mean that u and v have to be the same thing. And that will be enough to show that you have a unique solution, because if you had another solution, it would have to be the same one. Now, w is also continuously differentiable, which means that its derivative exists and its derivative is continuous, and it inherits that property from u and v being continuously differentiable. And it also satisfies the boundary value problem from the maximum principle. So we can move that over here. So w is continuously differentiable and satisfies the boundary value problem here. And so, by the maximum principle, so let's write that, by the maximum principle, w attains its maximum at t equals 0. So this problem here doesn't have an initial condition. So what is the initial condition of w? Well, w at x comma 0 is going to equal u at x comma 0 minus v at x comma 0. And u and v are both solutions to this problem up here, and where we're given our initial condition. So u of x0 is f, and so is v of x0. So we can write f of x minus f of x equals 0. And that's for all x between 0 and L. So the function w starts off when t equals 0, all the values on the wire are 0. So that means for all x and all t, we have w of xt is going to have to be less than or equal to 0, because we can never get more than where we start off at t equals 0. And of course, w is u minus v, so then what we get is that u of xt is less than or equal to v of xt for all x and t. Okay, so that's like half of what we needed. We really want u to equal v, but we've got at least that u is always less than or equal to v. So now let's go to another color. Now, that's kind of hard to write with. We'll do black. Now let, say, w hat equal v of xt minus u of xt. And by the same argument, we have that, w hat is a continuously differentiable solution to the initial, or to the boundary value problem, and we have the maximum principle. So by the same argument, we find that w hat of xt t is less than or equal to 0 for all x and t. So that means that, let's see, that means that v of xt is now going to be less than or equal to u of xt for all x and t. So we've got u is less than or equal to v, and we've got v is less than or equal to u, and so we conclude that u and v are exactly equal. So u, or whatever, also t, or also v, is a unique solution. So that is how a uniqueness proof typically goes. So the other part of that we mentioned at the beginning is that we also need a proof that a solution exists in the first place. Because uniqueness doesn't mean much if you don't have any solutions to be unique. But that's something left for another book. And so this is sort of the gist of it. This is all we're going to talk about on the heat equation from the book. And that's actually about it for the material from the book. So goodbye.